Hello everyone, this is Wale Saad. Let's continue discussing problems of assignment 2. In problem 14, construct a polynomial of order 4 using the Lagrange interpolation based on the table of data listed in problem 12. Let's recall the table of problem 12. Here is a huge number of points. If we need to interpolate it into polynomial of order 4, think about the minimum necessary property we discussed in the previous problem. So how many points do we need? For interpolating into a polynomial of order 4, yes, this is the n. So we need n plus 1 points. So how many points do we need? Exactly 5 points. Let's select any successive 5 points. I selected the first 5 points. And then what is required? The Lagrange interpolation. Remember the Lagrange interpolation polynomial? Yes, we will indicate it. So it's of fourth order. So it's y0 L0 plus y1 L1 plus y2 L2 plus y3 L3 plus y4 L4. What is the next step? Yes, it's to commute and drive the L node L1, L2, L3, and L4. Start with L node, where we will avoid using the X node at the numerator and then use it successively in the denominator. So the numerator of L node is the product of x minus all values except x node. X minus 0.6, x minus 0.8, x minus 1 times x minus 1.2. In the denominator, we will use this x node, the same term of L node, and then 0.4 minus 0.6. Of course, we will not use 0.4 minus 0.4. So 0.4 minus 0.6 times 0.4 minus 0.8 times 0.4 minus 1 times 0.4 minus 1.2. So here is the polynomial, and substituting in the points using x1, x2, x3, and x4, and then rearranging this by distribution of this constant, and then multiplying every two brackets, and then the product here multiplied by the third, and what's output multiplied by 4. Of course, these are algebraic steps that are trivial to all of us. Just be careful and be patient, of course, and then rewrite it in a decent form of polynomial with order 4. This is the first Lagrangian polynomial. Moving to L1, the same thing. We will avoid using x1, so we will multiply x minus x naught 0.4 times x minus 0.6 times x minus 0.8 times x minus 1 times x minus 1.2. In the denominator, we will use this time the 0.6. So the 0.6 is minus 0.4, and then 0.6 minus 0.8 times 0.6 minus 1 times 0.6 minus 1.2. Multiply the numerator and deduce the constant of the denominator. And here, after doing this algebraic rearrangement, we will get the last line. Again, for L2, we will use the x2 in the denominator and the x minus all other values in the numerator. Multiply algebraically and deduce the polynomials. Finally, we will substitute these derived L node, L1, L2 through L4 and scale them with the corresponding y values of the x of its term, and then rewrite it in that form. In part 2 of this problem, it was required to use problem 12, from where we got the table, that huge table of big numbers. Part E, we were using the interpolation of van der Monde for the same points. So if we evaluated the interpolation polynomial of van der Monde at x equals 0.9, and this deduced polynomial of Lagrange again at x equals 0.9, we can find that the absolute difference, or the absolute error that we call it, of course it's an accuracy measure, it's very small. Why do you think this error is very small? Of course, because we used small number of points. But if we increase the number of points, the error would become larger and larger. But of course, this is not a general interpretation for all types of functions, because the number of points, of course, affect, and also the position of the points from the beginning, from the middle, from the end of the table also varies the polynomial and reflects into the error. Okay, let's recall the Horner evaluating using Horner in evaluation. So we are ordering here all the coefficients 8.685 and the second, the third, and so on, all the coefficients in blue here in the first line, and then the 0.9, which is the value or the x node. We will multiply first, the first coefficient is dropped as it is because it's added to 0. Here we did plus 0, so it's dropped as it is. Okay, what about the second step? We will multiply this first coefficient by 0.9. Multiply, so we multiply these two numbers and equal, the equal stated here, this number will be written, and then we will add it to the third degree coefficient, this addition, and its equal is below here. And then again multiply this value with 0.9. The value will be written here, added to the above coefficient, and then write it down. Multiply again with 0.9 and so on. It's symbolically written here. So this is the B5, which is the same as the fifth coefficient of x power 5. And then we will multiply this B5 by the x node plus the A4 or the fourth, the x power 4 coefficient. And then here the x power 3 coefficient is added to x node, which is the term, the 0.9, the value, the arbitrary x value that we are dealing with the B4 or the value we got here, and so on till we find here the P sub 4 of the 0.9. So this is the evaluation of the fourth degree polynomial at x equals 0.9. And of course, this polynomial were deduced from the Lagrangian method. Thank you for your attention. Goodbye.